First, homework 1 is due this Wednesday midnight. So I already saw many submissions. If you have any questions, feel free to email me or the TAs. We're here to help. And this Friday, we are going to have the second quiz, 15 minutes in class. And the quiz will only include the crypto basics. So basically, the lectures from August 29th to September 9th. So we are going to ask questions about classical cryptos, modern, symmetric, modes of operations, Diffie-Hellman, and some questions about hash functions. So it's this Friday. So last class, we talked about IP spoofing, how IP spoofing can be exploited, and also a fragmentation mechanism in IP and how that can be exploited because of some software vulnerabilities. So we know that IP is not secure. It's not secure because when they designed IP protocol, they were not thinking about security. At that time, when they designed the protocol, the whole network was trusted. Not only the hosts, even the users, they are trusted. Security was not a problem at all. So basically, the problem with IP is there is no data integrity, no confidentiality, no encryption to protect the IP headers, no encryption to protect the IP payload, include TCP, UDP, or any user data. And the IP address can be spoofed. So there is no host authentication. So in this class, we will give an overview about IPSec. So Wednesday, we're going to talk about the mechanics, and today only an overview. So this class will be kind of short. So IPSec is the internet standard for network layer security, because it's the network layer security, which means is below the transport layer and above the data link layer. Because of that, it's below the transport layer. It's transparent to the applications. So you develop an application, and you don't even care if the operating system is running an IPSec. If it is, your application's communications is protected, and your application doesn't need to change anything. And because of this is also transparent to end users and can provide securities for individual users. Basically, IPSec protect integrity and confidentiality of IP packets. So, and it can also verify the source of IP packets, but that part is also related to how you distribute your keys. So when they first designed IPSec, they actually designed it for IPv6. So it was part of IPv6. But we know that we're not really using IPv6. And fortunately, when they designed IPSec, they made it compatible with IPv4. And in this class, when I talk about IPSec, I will use mostly IPv4 as the basis to discuss IPSec. So IPSec, because it's above the data link layer and below the transportation layer, so it's not tied with the data link layer. It doesn't care what kind of physical medium you are using. So it's applicable to use over local area networks and also across public and private networks, and also for internet, because the internet, they are talking using the IP protocol. So IPSec provides the protection between host to host. The two hosts, they do not have to be in the same private network. They can be, but they don't have to be. And also host to gateways. Gateways here means the middle boxes, including routers and also firewalls. And it also provides protections between gateway to gateways. So gateway to gateways, they also have their own protocols, like routing protocols, to exchange routing information. And those information is also using IP, so they can be protected by IPSec. But in this class, we're not covering routing protocols. So like we discussed last week, the IP protocol is like the highest level of protocol used both at host and middle boxes like routers. So routers can also be protected by this. So IPSec itself is very complicated. It's a suite of protocols. The main components, there are three. One is called authentication protocol. One is an authentication protocol called authentication headers. Even though the name is authentication headers, it's not really only refers to the header, but also the protocol itself. It is defined in this RFC documents. And also another protocol that combine encryption and authentication is called encapsulating security payload, ESP. Even though this protocol also has a weird name like payload, it is actually a protocol. And we discussed in crypto basics, in order for you to build a secure communication, you need to somehow exchange keys. And so in IPSec, there is another protocol, another suite of protocol called key management and exchange protocols. There are many protocols in this category, and this is the default one. And actually, this one uses Diffie-Hellman to negotiate keys. So this authentication header and the ESP, those two protocols, both of them then can be used alone, but also you can use them together, combine them together. You can apply ESP first, then apply header authentication again. The reason you want to do that is we will explain this when we get into the mechanics of it. But now I will give you a sense why you may need this. So when you do an encryption, use an ESP, you may encrypt the whole IP packet. Because you encrypt the whole IP packet, the original IP headers will be encrypted. And because it's encrypted, the middle boxes, they don't understand what that is. So you need to add a new IP header so the middle box, the routers, can understand that, can forward those. And because of that, the new IP headers is not protected. So maybe you don't want to encrypt it, but at least you want to authenticate that. That's why you do an encryption with ESP first on the original header, original payload and headers, then apply a header, an authentication header on the new IP headers to provide authentication. So this is achieved by using some concept like security associations, we will talk about in a moment. So this is a comparison of the features authentication header and ESP can offer. So authentication header, it can offer data integrity. It can offer data origin authentication, basically to stop IP spoofing, but it's also related to how you distribute the keys. And also it can defend the replay attack. That's one option too. A replay attack means as an attacker, somehow you capture one IP package in the network, then you want to replace that to impersonate the original sender. So because authentication headers, there is something called sliding window. It can defeat replay attack. Basically, if you want to replay some message, it has to in this sliding window. Otherwise, the receiver side will just simply drop that. And the ESP with encryption only, it can provide replay attack because it's encrypted. It provides confidentiality and other features. And if you combine ESP with authentication header or ESP itself, you can use encryption and authentication. You can provide all these features together. So in most cases, we are using ESP instead of header authentication. So IPSec, one of the most important concepts is there are two different modes in IPSec. The first one is called transport mode. So transport mode provides an end-to-end security between any end stations. So we have a network here. This is one host. This host might be in a private network connected to router 1. And eventually, through a lot of routers, it wants to talk with another host very far away. And those two hosts, they can establish an end-to-end encryption secure channel using IPSec. And this is called a transport mode. So in this case, all the communications between the sender to the first router, from the first router to the second router, and from the last router to the receiver, they are all encrypted and authenticated. So the routers in the middle, they do not see the content of this message. They just forward this message. So if there is any attack at all those links, they can be defended. But the problem of this is if this host wants to establish a collection with many, many other hosts, it has to establish the one secure IP collection with each of them. That would be very expensive. So this transportation mode, sometimes they are also used between end stations and the gateways. But in this case, the gateway is actually treated as a host. So the gateway could be a router, could be a firewall. In this case, they are treated as a host, which means you are only using this the gateway in this case is actually the destination. For example, you want to SSH or Telnet. Yeah, Telnet might be a better example. If you want to remotely control this router, you can do it by creating an IPSec channel transport mode between your host and this router. So in this case, the router is not actually forwarding your packets. It's the destination. So it's still end-to-end secure communication, and all the links between this host and this router, they are encrypted and authenticated. All the attacks on those layers will be protected. And another mode is called internal mode. So internal mode, mostly they are used for gateway-to-gateway communications or host-to-gateway communications. So why do we need gateway-to-gateway communications in this internal mode? So previously we talked about that the routers, they are going to communicate with each other. They are going to use, they are going to exchange routing information. But in those cases, the routers, they are more like destinations when they exchange routing information. So they are still using transport mode to secure that to secure those communications. But if a host, in this case, still it wants to, let's say this is your home network. This is your host, and this is your home router 1. And this is your office network. There are many hosts in the office network. You want to establish a secure communication between your host to many of your servers in your office network. you can establish a end-to-end collection with each of them. But it's very expensive. A better way to do that is you establish a internal mode IP collection between your router and your home router and your office router. So it forms kind of like a private, virtual private network. So your host here, even though they are physically isolated, not isolated, physically separated, this node you're at your home feels like it's in the same network as other computers in your office network. So when your computer wants to talk with any other servers in your home network, in your office network, it doesn't have to establish an end-to-end collection with each of them. The encryption will only be between the routers. So if there is some insider attacks in your office network or some insider attacks in your home network, this will not defend that. However, in most cases, this is what we are using for virtual private networks. So all the companies, they are using something like this to collect their sites at different locations. So Microsoft, they have a Seattle office and they have office in Beijing, so they want to collect them together. So they are using something like this to form a virtual private network. So this internal mode can also be used between host to gateways. So but in this case, in the host, you have to run something kind of like a proxy. This proxy behaves like a router. So technically, you are still using the gateway to gateway mode, but you are running your own gateway on your own host. In this case, you can. So even the link between your host to the first router is encrypted, and all the attacks at here or between the routers can be defended. However, still, if your home network there are some insider attack, we cannot defend that. So why we want to use something like this? For example, if you are traveling, you only have your computer, and you want to connect to ASU's network. So obviously, you don't trust, you are in some hotel, you don't trust the hotel's router. You cannot ask the hotel's router to establish a secure communication between our ASU router. It doesn't make sense. So you are running something as a proxy on your host, and this proxy establish a secure channel between our ASU router. So this is normally what we use when we travel. And like I said, this internal mode is mostly used in virtual private networks, and they are physically distinct network, but internals are created and encrypted to provide confidentiality and secure communication channels between them. However, IPSec is not the only technology we can use to build a VPN, but since we are starting from lower layers to upper layers, IPSec would be the first one we can use to build a VPN. So here is one example. Alice works for the mergers and acquisition department of one company. So she's on a business trip, taking over a plant. So she wants to access the M&A servers and other servers at her company. So obviously, what she's doing is confidential. She wants to build a secure communication channel. So which IPSec mode is most convenient for her? Which mode should she use? We just talked about this. Transport or internal mode? Internal. So transport mode also works, but it's not the most convenient way because she has to collect to each servers individually, and she wants to collect to many servers, so it's not convenient. So internal mode we talked about two cases, gateway to gateway and host to gateway. So which one she's going to use? Host to gateway. So she's running some kind of proxy on her local computer, and that proxy will behave kind of like a gateway to establish a secure communication for her. So we're going to take a look at how the transport mode and turtle mode, they actually package they wrap the package. So this is the original IP package, not encrypted, not authenticated. We have an IP header and some payload. Maybe in this case, we have TCP headers and also user data. So in transport mode, the original IP payload can be encrypted. So only the IP payload part can be encrypted, not the IP headers. So the IP headers will almost stay the same. There will be some little changes. For example, the IP length. There is a length field to say how big is the IP. We have to update those, and also the checksum fields. We have to update those. But the payload part we'll put here. Then we will encrypt the payload part, the IP payload. But how do we know how to decrypt this? We cannot change the IP headers, because if we change it, the router doesn't understand how to forward it. So we will add an IPSec header. And this IPSec header will specify what is this payload here, and what kind of encryption algorithm we are using to encrypt this part, how you should decrypt this. So in transport mode, one IPSec header is inserted between the IP header and the IP payload. And the IP payload would either be encrypted, authenticated, and the IP headers cannot be encrypted, but it can be authenticated. And internal mode, we're putting the entire original IP packet as the new payload. So we call it the inner IP header. Then we encrypt the whole part. Because we encrypt the whole part, we don't have an IP header anymore. The routers, they don't know how to forward this. So the router has to create a new IP header. And this IP header cannot be encrypted. It has to be plain text. And also we have an IPSec header, which specifies what encryption we are using. So the receiver side, they can decide how to decrypt this. So the IP header in this case could be either using the authentication header protocol or using the EPS protocol. So you can say if we are using the turtle mode, gateway to gateway, so when you send out an IP packet, your packet will be like this. And this packet arrives at the router, the gateway. Then the gateway will take the whole entire packet here and encrypt it, and add two more headers in front of it, and send it out to the receiver's router. And the receiver's router, so the IP headers here, the IP source address, and also the destination address would not be the same as the original IP source and destination address. When this turtle mode packet arrives at the receiver's router, the receiver will check this IPSec header to say how I can decrypt this. After it figures out how to decrypt it, it will decrypt the whole payload, and it will forward this payload to its own network. So it's kind of like there is a tunnel between two physically separated networks. And the tunnel is also encrypted and authenticated. Yeah.
So in host to gateway, the gateway that encrypts the packet would be the virtual gateway that the VPN software creates?
Exactly. So in the host to gateway like the row like a gateway. So it's actually the same. So like I said, IPSec is an internet standard. It's very complicated. I'm trying to give you some abstract, so it will be easier for you to understand. So in the specifications, they define many concepts. The most important one may be the architecture of IPSec. So in IPSec, each communication entity is called an IPSec module, and the IPSec module can manage the security for individual collections to other modules. So each collection, they are using different keys, different key requirement, different, which is called security associations. So first, because this is widely used in corporation, so they have something called a security policy database. So this security policy database provides specs of security services to be applied to each packet. And excuse me. And then they have a security association database which contains the security parameters such as encryption algorithms, what kind of operation mode we should use, the initial vectors, the session keys to be enforce specific policy. We will talk about, we will give some example in a moment. And also each collection from one module to another is associated with some kind of parameters. And those parameters, they form a security association. And the security association database is used to store that. So note that security association is unidirectional, which means if host A wants to communicate with host B, bidirectional communications, then there are two security associations. There are two keys used to, one key used to encrypt all the communications from host A to host B, and another key used to encrypt the message from host B to host A. So even if one of the communication channel is broken, the other one might still be safe. So this is one IP module. It could be your host, it could be your gateway, or it could be a proxy on your host, and this is the other one you are trying to talk with. So security association is an association between a sender and a receiver. So they share this security association, which includes the keys. So this security association consists of some parameters. The most important one, obviously, is the encryption key. We're assuming we are using symmetric key here. And also there are many other parameters, sequence numbers, initialized vectors. And we said this is a one-way relationship. And this security association, it has to be new for each communication. It should never be reused, especially the key part, to keep this system safe. So each SA is uniquely identified by three parameters. The first one is called a security parameter index, which is like the index you use in a database. So this index identifies, it's just a random number or random string to identify this SA. Why do we need this? Imagine we are doing a secure communication. Before that, we are not sending we're not sending the session keys because the session key is a secret. We cannot send it over through some unsecured channel. So probably we are going to negotiate that with Diffie-Hellman. But after we negotiate that, your host may have many IPSec communications with other hosts. How can you identify which session key I am using for this collection? So somehow you need to associate an ID with that key. And that ID, we call it security parameter indexed. And also, in this index, it also carried because there are two protocols, AH and ESP headers, to allow the receiving part to select the corresponding SA. So the receiver part, they can use this to decrypt this. And also, IP destination address is used to identify a SA, because even this secure parameter index, it should be random, it should be secure, but it's possible there are two collections, they accidentally using the same index. So in that case, we also use the IP destination address to separate them. And also, we can use, if this is this association is for authentication headers or it is for ESP headers. So we discussed that it is possible to apply two layers of IPSec. You can do a ESP first, then do a AH. And when you do that, you are using two different SAs, because each SA is associated with one layer of protection. And when you do that, this is called a SA bundle. So all the SAs, it includes the encryption keys, the index, they have to be stored on your local host or on the gateway. So basically, you have to store that on the entity that is using IPSec. So they are stored in this database called a Security Association database. So this database holds parameters for each SA. First is the SA itself, the index, the encryption key, and also some metadata, something like lifetime of this SA, the timeout, the timeout we should use. And also in this architecture, we have the policy part. So the policy part is managed by administrators of the network, or if you are using the transport mode collecting to another host in the network, then you are managing policy by yourself. But why this part is important? Why do we need policy? Because this IPSec kernel mode is mostly used for VPN, and the VPN are mostly used for big corporations to collect their different campus at different locations. So they need a very consistent policy. So the policy will decide what kind of traffic we should apply IPSec, what kind of traffic we want to protect. And also will decide the incoming traffic, whether it is protected property. If it is not, maybe the policy will say, because this message is not encrypted, we will just simply drop it. And the policy will define which security association or SA bundles to use for each IP traffic. And each host and gateway should have their own policy database as well. So if we are using gateway to collect our different sites, actually we only need maybe several policy database on the gateway. But if you are doing a host-to-host collection, each host has to maintain a policy database like this. So I will explain how this policy work and what it looks like. So basically, the policy will decide for an incoming packet, the policy can specify, do we want this package in, or we only want to drop this package. So this provided a basic firewall functionality here. And it can also specify if there is an outbound packet, maybe we don't want to apply IPSec. And if there is an inbound packet, even if it doesn't have IPSec protection, we want to accept it. But most importantly, it will specify for an IP package in and out, how should we apply IPSec on this package using different security associations. So here is a policy example. So if this is your company network, and this gateway has this policy which says all traffic to this network must be use IPSec. Maybe because this is the gateway of our company's a network at another site. So all the traffic to this IP or this network has to use IPSec. And we have to use pre-hashed key authentication. We have to use DH-Hillman protocol. And the hash algorithm has to be this algorithm, and the encryption has to use this symmetric key encryption. So basically, the policy will specify to what destination we have to use IPSec, and when we use IPSec, what kind of parameters we have to use for this collection. And when this English policy is translated into IPSec policy, it will look like something like this. Yes?
I'm kind of confused with it. Does the Diffie-Hellman group use the hash algorithm? So like it'll come up with the number and then...
No. So the DH is used to negotiate the session key.
Right.
So the hash algorithm is used for integrity check and authentication.
Okay.
Yeah. So here is an example of the policy database and a security association database. So in this case, we have a host A trying to talk with host B. They can talk first with a transport mode. In this case, A's policy may look like any packet from host A to host B with any protocol to any port, we should use authentication, and we should use this algorithm, hash MD5. And another policy, this is a policy level, and at the security association level, we have to give what kind of keys we need to use for this hashed MAC. So in this case, it will specify, oh, this is the key for this policy. If we are using internal mode, host A wants to securely talk with host B, so actually the secure communication is between the gateway C and gateway D. So the gateway C's policy may look like any IP packet from host A to host B should be encrypted using ESP, using 3-DES algorithm, and the destination of this tunnel is gateway D. And this is a policy, and the security association should specify what kind of key is actually used. The session key is actually used for this ESP. So the association will look like something host A, from host A to host B using the ESP protocol, and this is the key index, and this is the actual key. So it's possible that when we send out a message, we want to apply some kind of a security association, but the receiver side doesn't have the same security association because we haven't negotiated the key with them. In this case, when SA doesn't exist, the outbound, it will trigger key management protocol to generate SA, and the key management protocol will include the procedures to negotiate the key with the receiver side. Or you can manually configure this. And for inbound processing normally, which means this is not a collection we are expecting, we will simply drop this packet. So here is an example. We have an IP packet, and first we will check, should we apply IPSec to this package based on the destination, the source, based on our policy. If the policy says, okay, we should use IPSec for it, then it will determine which security association we should use by querying the association SA database. And from there, we can get the actual session key. Then the IPSec protocol stack will use that session key to encrypt the IP packet and send it to host B. So when host B receives this packet, because this is encrypted, it says this is a IPSec packet. It will first query the SA database to see if we already know the session key of it. If it knows, use the indexed, it finds the key, and then it will check the security policy database. Is there any violation of this packet? Is it using the encryption algorithm we negotiated before? If everything is correct, it will decrypt this packet. The IPSec protocol stack will decrypt this packet and get the original IP packet. And this packet will be sent to upper layer applications to use. So any questions? There are several concepts here might be very confusing. So what is the most important thing for encryption? The key. You need somehow exchange the key. And because there are multiple collections, you need to identify which key you are using. So that's why there is a security association. So basically the security association is the key and an identifier of the key. So with that identifier, you can query the security association database to find the key. And at another layer is the security policy, which is we are using it because the protocol, the standard is trying to solve real-world problems, and they are trying to be very comprehensive. But if only two hosts are communicating with each other, you don't really need a very complex policy. But for a company, you can imagine there are many complicated policies. Everyone is following? Any questions?
So all of these security association databases stuff are kind of just a way to abstract security, where you just look at these squares in the architecture. You don't really have to figure out what's inside.
Yes. So they have to be used in all the gateways and hosts that they want to use IPSec. So in this class, we talk about the overview of IPSec. So I hope this is not too confusing. So the next class, we're talking about the mechanics. We're going to look at the authentication headers and the ESP headers and how the key negotiation actually works.